Good morning, everyone. So my name is Tuhin Ghosh. So I'll talk about lesson learned on CMB foregrounds from Planck and BICEP. So these are the two experiments that I was associated with, Planck and BICEP experiments. So Planck stopped working in 2013, and BICEP is still taking data. So before I start, I'd like to thank the organizers for having me here. So we should introduce CMB. So I'm experimentalist or like observer. So basically, how we can measure the CMB from ground or space. So Planck is like third generation CMB experiment, which try to measure the CMB spectrum. But it's not the first one. Before that, there was a WMAP and Kobe. So this CMB and measurement of CMB and anisotropic started from 1990s. And in future, there are two experiments which are proposed for Planck. One is Lightbulb, which was planned to launch in 2032. And from ISRO also, there is something which is planned by the CMB community, which is CMB Bharat. So this is from the space, so basically to get the large scale CMB modes. But on the ground also, there are lots of experiments which are targeting the small scales to learn about the universe. So there is a Simon's observatory which is functioning now and is taking the data. There is a SPT and ACT which is collecting the data and the BICEP experiment. So my talk is mostly focused on BICEP and Planck, but the techniques and all the things that I'm going to talk about is valid for other experiments also. Okay, so basically the goal of cosmologist or the dream is basically to measure this spectrum very accurately. So this is the CMB spectrum from the temperature. So basically there are noise or foregrounds, so you have to minimize all those to get these points very accurately. So these are the data points, and then there is a solid line which is the model. So this model depends on, so currently our understanding is the Lambda-Sedgwick model. But if you want to look beyond the standard model, you want to measure this spectrum very accurately. So this is for temperature, but the temperature now is, information is exhausted. So it's the experiment given one sky. Whatever looks we can measure, we already got it with Planck. So now focus is mostly on the polarization part. So CMB is like 10% polarized. So we measure the polarization because it's linearly polarized. We measure Stokes parameter Q and U, and we convert this into E and B modes. So with Planck, we measure this E spectrum very accurately from 30 to 1500. So at large L there is error. At small L also there are large error bars. So given this error bar, it's hard to constrain the cosmetic parameters. So like ether restoration, which depends on this low L measurement. And so basically what in the next generation experiments are targeting is to measure this as precisely as the CMB temperature. Okay, so this is the E mode power spectrum, but we can do all the cross. So there is a TE power spectrum, which is measured very accurately. There is a EB spectrum, so we can cross with E with B. So ideally, if there is no parity violation, it should be 0. But with Planck, it is finding some oscillatory pattern, which gives hints about the early dark energy model. So currently, the goal is to measure this EE, BB, and the BB spectrum to as precisely as possible. So this is the proposed Lightbulb experiment. What it will do? So where the errors are large, basically the next generation experiment is targeting to minimize the errors and try to measure those. So my talk is mostly focused on this BB power spectrum. So this BB power spectrum that we measure has two parts. One is the primordial B mode, which is basically tracing the primordial gravitation waves. And there is a lensing B mode, which is the leakage from E to B. So if you can measure this lensing B mode, or make a map of lensing B mode, we can directly measure the dark matter distribution of the universe. So that is one goal. Other goal is to measure this primordial gravitational waves. So basically all the future experiment is targeting this B mode power spectrum. So you can see there are large error bars, so you want to minimize those. So that is a dream. So basically you can set up an experiment and measure those. But the challenge is that when we do the experiment, it's not that we can see only the CMB. There are foreground emissions from our own galaxy. So this galaxy emits in microwave frequency. So if you look at one frequency, you can will not know whether it's a foreground emission or background emission. Okay. So what people do is they measure not in one frequency but in multiple frequency to separate out what is the background emission and what is the foreground emission. Okay, so the low frequency, it is mostly dominated by radio emission or the synchrotron emission, which dominates at low frequency below 30 gigahertz in that frequency range. At high frequency, there is a thermal dust emission. Okay, so which dominate above 100 gigahertz. So if you look at 545 gigahertz, it's totally dominated by thermal dust. So CMB signal is like very less there. But we do this multi-frequency observations to basically know what is the background and what is the foreground emission. And it is not at large scale. So it is there in all the scales. So at large scale, these are diffuse emission. But if you go to small scale, there are extragalactic emission like cosmic infrared background anisotropies, molecular clouds. There are point sources like the radio point sources, infrared point sources. So there is no clean band or clean scale where we can just observe the CMB. But for temperature, we at least the background we can see, which is constant in this thermodynamic units, and whichever is fluctuating is like changing is basically the foregrounds. So this is for temperature. For coloration, the story is same, but unfortunately for coloration, we cannot see the background. So everything is within the foreground. So we need to subtract the foreground emission to get to the CMB. Okay. So basically goal is to take those observations and remove the foregrounds in some component separation way and measure this intensity Q and U map, which is clean from any foregrounds. So once we have Q and U, we can make polarization angle, what is like how the angle is related to the structure, or in terms of E and B, which will help to help in the cosmological parameter estimation. So that is basically the goal. So now there are two different kind of foregrounds for B mode study. One is synchrotron polarization, which produces B modes. So the synchrotron polarization is basically coming from cosmic ray electron, which is gyrating around our own galactic magnetic field, which is order of microwatts. So this is theoretically 70% polarized, but what we observe because of the projection effect is typically like 20% polarized. And people model this using a power law model. So this Q and U, it follows this power law index beta S, and this beta S we know to very high accuracy, but it's not enough to go to the wind. So there is a region to region fluctuation which is causing problems. And this simulation, we cannot do it at very low frequency because there are Faraday rotation. So there is a lambda square dependent terms which will correct this synchrotron polarization. So it's very, like if you go to like 1 gigahertz, it's very hard to measure at the galactic plane what is the synchrotron polarization. So people generally measure this above 10 gigahertz to get a good template of synchrotron polarization. So this is one of the dominant foreground. Another is the dust polarization. So these are basically small dust particles made up of carbon and silicates, which is basically gyrating around the magnetic field, and it will basically in optical, it will absorb this light and emit in infrared frequency. So people initially thought that it is not be that much polarized. In BICEP they consider it like 2 or 3% polarized, but what is observed with Planck is that it can be polarized up to 20%. So this is observed polarization. In this way it is more polarized, but because of coalition effect we see this 20% polarization, and this follows a modified black body spectrum. So it's a power law, but there is a temperature dependence. So we need to know what is the temperature of the dust. So now I'm just plotting the CMB spectrum that we are targeting, and on top of it, this foreground emission. So this is taken from Science Observatory science paper. So basically, if you go from 1% to 90% of the sky, so there are some clean regions where you can measure this lensing beam width above the foregrounds. So this is good news because we don't need to deal about the foregrounds, which are complex nature. But for primary beam width, so here from R of 0.01, any region we go, there is a foreground which is dominate over the signal. So without the foreground separation, we cannot measure the CMB beam mode. And to separate the foreground, one frequency channel is not enough. So we at least have 2-3 frequency channels to know what is the foreground and subtract it to get to the signal. So this is what was the initial idea of Lightboard. So this was proposed by Katayama and Komatsu in 2011. So they thought that if you do 3 frequency channels like 60, 100 and 240 gigahertz, and if you know what is the spectrum of this synchrotron spectrum and the burst, so one is power law, one is modified black body spectrum. So using 3 frequency, we can just subtract the synchrotron and the dust part, and we can achieve the target sensitivity of -3. So that is started the Lightboard discussion, and now it is like in a almost mature stage, which will fly in 2032. But this is a model dependent approach. So these models are derived from the data, and we don't know what is how accurate these models are, because these are simple analytical models. And if the complexities, like if it's not a power law, it has some curvature, or there is not a modified blackbody spectrum, is there a 2 modified blackbody spectrum? Because of the error bars, we see only the 1. So it will, if the model does not match with the data, then these foregrounds will leak into the CMB estimation, and it will give you false detection of the CMB signal. So this was shown by Remazillas in 2016 paper. It maybe there are, we are considering the dominant ones, maybe there are other foregrounds which are not that dominating, and if you neglect those, it will leak into the CMB and it will produce a fake signal. Yeah. So, so that if you do it pixel by pixel, it is difficult. So what is the approach taken by the BICEP team? So they basically, instead of looking at pixel by pixel where the signal to noise is a problem, so you can compute a power spectrum. So then you can increase the signal to noise by taking a lot of pixels, and you can fit a model which has a synchrotron, dust, and it can be in the power spectrum level. The synchrotron and dust can be correlated. So that is taken by this rho indices. So we can fit with this model of foreground plus some primordial beam mode R and some amplitude of the lensing signal. So this is a 7-parameter fit which was done by BICEP from 2015. So I will show the result, but basically this model, if you do it, is simple. The problem is that all these are almost like power law, so it's degenerate. So unless you put a prior that what is the value of typical value of beta S, beta D, is very difficult to get a unique solution. So there basically Planck comes into the picture. So from Planck we have a large scale mode. So we can measure what is the spectrum of dust on the synchrotron at from the large scale. So what is found is that this dust, they follow nicely power law. So this is one is the E power spectrum and one is the B power spectrum, and this E to B ratio is roughly constant. And this T spectrum is this correlation with E is also roughly constant with the sky fraction. So if you can write whatever the complex information of dust into this power spectrum and derive into simple mathematical form, it helps in the component separation. So we found that it is following a power law, and this power law has some index which is normalized at L is equal to 80, and if you decrease with the sky fraction, it follows a nice power law model. It follows like I to the power I square relation, and the BICEP point is here. So it is within this cosmic variance. So whatever the dust which is expected from the large sky fraction, it applies to the BICEP patch. And this EB spectra, which people are interested for early dark energy model, so this dust also produce this EB, non-zero EB. So this is something new. So when somebody claims that from CMB we are measuring EB spectra, we need to be careful that it's not the foreground leakage. So it can be the foreground which leaks into the CMB and can mimic a wrong early dark energy model. So, but the EB spectra, this TV spectra is consistent with 0. Okay. So this correlation between dust and CIB, dust and the synchrotron, it shows up. It in the power spectrum. So at high frequency, it is a modified blackbody spectrum. At low frequency, it is a power law. And then when you do cross between high frequency and low frequency, there are some points which shows up here. So that is a large scale effect at low L. But when we go to high L, it decays down. So this dust synchrotron correlation tells about that they are basically tracing the same underlying galactic magnetic field. So that's why even the source is different, because the same galactic magnetic field is tracing. So there is a large scale correlation between them. So similar thing can be done with synchrotron also. So what is found that at low frequency observation, it also follows a power law model, and there is a E to B ratio, which is like or B to E ratio is like 0.2. Yes, I will finish. So from the spectrum, if you have multi-frequency observation, we can measure what is the spectral index, and the synchrotron is depending on the sky fraction, it is roughly constant. So, but then there are small error bars on top of it. Okay. So these are the simple model, but then it can have a decorrelation. So it's not the correlation when we observe, it's not the same pattern that we see in different frequency. So the pattern can change, and it will mimic like a decorrelation. So this cross, whatever the power spectrum, it is less compared to what is expected from 2 auto power spectrum. Okay, so this is first detected by Planck, that if they detected like 2 sigma in each mask, but if you consider all the masks, it is like greater than 5 sigma detection, and this is a problem. So in the previous analysis, this decorrelation was not considered, that the pattern can change with frequency. So ideally, larger frequency will not help. So you need to have more frequency channels in a very closed band. So for current CMB experiment, this is one of the major challenge to deal with the dust decorrelation. So if in the power spectrum level, if there is a SED variation that is not constant, SED is varying pixel to pixel, because we are taking the power spectrum average, we can write in this form, but in reality we don't know if this form is true or not. And the result that BICEP is claiming that R is less than 0.06, it depends on this dust decorrelation factor. So, so this value is without taking into account decorrelation. So once we account the decorrelation, the value shifts from the value to a lower value. So currently it is not detected, but this is one of the main concern of all the CMB experiment, how much dust decorrelation is there. And at least 1% we expect, and even 1% is problematic for this value of R. Yeah. So just last few slides to flash the images. So in BICEP result from 2015, they only consider dust and the CMB. So from that they get a measurement of some likelihood that this is the value of R. When they collect more data at the lower frequency, they start seeing the synchrotron. Okay, so once the more foreground is there, the value of R shifted towards close to 0. They collect more and more data to get a confidence that to shrink the error bars. But what is happening is that error bars is shrinking, but the value is shifting towards 0. So this is including 150 and 220 gigahertz, and then suppose the synchrotron, if you collect more data, 95 gigahertz with BICEP 3, the value is stabilizing, but it is whatever the original value from 15, it is 21, it is shifted to close to 0. And this is not including the decorrelation in the formalism. So even include decorrelation, it shifts bit to the lower value. And this implication is that this R says what is the model of inflation. So with the more precise measurement, we can start ruling out more simple model of the inflation. And with this, thank you. And this is a summary of my slides.
Hi, Tukin. Thank you for the nice talk. So at some point you had showed that the dust also had some alignment with the magnetic field. And I think the dust tries to align with the magnetic field. So in which case, like, wouldn't if you measure the synchrotron and the emission from the dust, wouldn't they be correlated in a sense? Then you have like one less parameter.
But there is a line of sight effect. So dust is a local dust, so which is connected with the magnetic field that we observe.
Sure.
But the cosmic ray is tracing the full galaxy.
Right.
So, but you see the integrated effect for the synchrotron. So it's not one-to-one correlation.
So if you look at the synchron spectrum, like you get the spectrum by just doing that synchron calculation, and since you know the chemistry of the dust, that will already tell you like what the spectrum you expect. But these two things at least alignment
Locally it is correlated.
Right.
But we are seeing the integrated effect. So we don't know from where it is coming.
I see.
So for synchrotron, we are seeing a larger path length, and for dust, it is a localized because it goes as 1 over r square. So whichever is far away, it will not contribute to the dust emission or the map we see. Okay. But locally, it is correct.
Okay, thank you.